logistics and moving packaging around there. So this is our little airplane before we got involved in it in 2009. It's maiden flight, and since then it's been flown about 6 times, and we're setting it up now to prepare to fly much larger cross countries here in California, and then slowly but surely moving so where we can fly it across America with no one inside. Our control system, strangely enough, is designed and built using the basic telemetry and the basic components that are off-shelf components for for existing autopilot programs. And in this, we're building a different controller system right now, but actually the controller system that existed for the autopilot was really pretty good. Radar altimeter was one of the best that we could find. So there was a lot of really important things that we didn't really have to do. A lot of it was just off shelf. And this is the aircraft. You can see here the aircraft having a successful landing. And as we're showing here that it's a Cessna Skywagon, we show here the aircraft coming in and landing on its maiden flight. And it was a pretty amazing thing. So now I'd like to talk a little bit about the FAA. I kept this one page for it because all that at the top, that chaos at the top, are all kind of the terms and the acronyms that are used for God knows a million different things in the FAA. Plus, there's probably thousands more because it's they've been a cross between the military and a cross between commercial use for so long. What the FAA is now doing is they have moved fast. Although they were originally supposed to, for 2015, they were supposed to launch and have full integration and completion of drones into the commercial airspace or into the NAS by September of 2015. They missed that date. So it looks like in July this year that's going to happen. We're very close now with the FAA. We're fortunate enough to get to talk to them a lot. They're definitely doing everything they can do to perform to make sure that they launch the program. And what the program is based on is the Part 107. And the Part 107 inside of that new package is that new rule is a list of products that have to do with flight, commercial flight, and etc. So I'm more than willing to, this is a kind of a boring subject, so if anybody wants to talk to me about it afterwards, that'd be great. This is the future of UAS. I've actually seen this vehicle up close. This is a human drone. You can jump inside this thing if you're really light, and you can fly across the sky, I guess. It's just a simple drone. It has a simple drone concept. It uses a controller from a DJI aircraft, so it's another Arduino controller. And this is an aircraft that we're doing right now with Spectrum Aviation, where it used to be a business jet. We're actually doing this with Linden Blue, and this will be a great aircraft that will be full of goods and fly from coast to coast in about 3 hours. And then, of course, this is a future transportation where we have one of these vehicles, and that's the thing we're really doing with drones. More than anything, what we're doing with drones is we're laying the footprint with drones to be able to fly in cities and make the real superhighways of the future. And those real superhighways of the future are going to be, because, I mean, governments can no longer afford to build infrastructure. We can't ask them to build another 405. It wouldn't work anyway, we know that. And so the thing's going to happen is we're going to have $300,000 Teslas that fly above all the traffic, and you'll be able to buy one. And it won't be any real infrastructure because we're building all that infrastructure right now, that digital infrastructure. That's what we're doing every day when we fly a drone. And then this is a really important shot I thought I'd show you guys. This is a starfighter, actually, in 1945 that crashed on a ship in the Pacific. No, not really. Just had to throw that in so you guys can have a laugh. I thought that was a great picture. That's a real drone there. Any questions? Yes, sir.
Questions toward the end of it, please?
Okay. Yeah. I thought we were going to do that.
It's an awesome presentation. Can I have a copy of yours? talk is a bit academic. I'm not a professor at the University of Illinois at Champaign. I will start, and it may take a bit longer than half an hour because I already saw so much I want to relate to every piece of that talk. So as I said, today we'll talk about aerial for robots, and to put things into perspective, I will start from my involvement with flight control technology, going into the history of flight control. So we got some of it here already in the first talk. And the main driver of our research was the certification challenge of flight control systems, advanced flight control systems. I will talk about some work with the transition to NASA, USA, Force, and other industries. A little bit we'll talk about cooperative control of unmanned aerial vehicles in the uncontrolled airspace. I'll describe a little bit what is uncontrolled airspace. And opportunities in commercial sector, like we heard recently about firefighters, about some other applications that we're involved with, and also interaction of humans with flying for robots, where we integrate already research from computer science, psychology, data science, and so on. So here are the examples of aerial for robots that some of you have seen already. So this would be kind of a surveillance machine that would do surveillance. This will capture data from your farms to help you get actionable insights. This Amazon Prime aerial delivery drone that we have seen. This is a type of vehicle that will work at NASA for aerial sampling. And what you see here is basically a drone reduced to wearable technologies. It's the Nixie drone that can fly and take a small selfie. And this is a snapshot from the New York Times article that were there where we developed kind of a drone for domestic use to help elderly with daily tasks. So to give a brief background on my kind of pedigree, so I graduated from Yerevan State University in 1988, pursued my PhD in Moscow, spent a year and a half in Stuttgart University, Germany, a year in France, and then in 1998 I came to Georgia Tech Atlanta. 2003 I went to Virginia Tech with a faculty job, and in 2008 I landed at the University of Illinois, where I have been since then. So as I said, my work with flight control technology involves a historical event. So in 1967, in the kind of mid-50s, 60s, NASA launched its X-15 program, which is until now the most prominent flight test program at NASA. So the objective was to bridge the gap between the manned flight in atmosphere and the space flight by flying at altitudes about 30,500 meters at Mach numbers 426, and it was clear that a single gain flight controller would not suffice for the large envelope and all the variations. So people started testing adaptive controllers, and the first one ended up with a crash on November 15, 1967. As a later study at Honeywell figured out, it was due to the adaptive controller that went into saturation and led to the crash. Later, Carl Ostrom referred to that period as brave era, implying that there was a very short path from theory to practice. Today, if you decide to crash an airplane like this, it's simply impossible. It's pretty safe for that. That historical crash led to massive research by mathematicians to establish the stability and robustness properties of flight controllers. And I won't go now through the details because I'm not in MIT or Berkeley. I'll just quickly jump saying that the historical developments along the theory line led to another landmark achievement. Exactly 30 years after that historical crash, United States Air Force, jointly with the Boeing Company, successfully flight tested the X-36 tail unstable aircraft with an adaptive controller on board. What basically this flight test proved that there is no need to do wind tunnel testing for modeling the aerodynamic coefficients, with an estimate of which at Boeing will run it to $10 million, and instead one can use an adaptive flight controller that can compensate for the lack of knowledge of the aerodynamic coefficients, yet the benefit does not come for free. Basically, if on one hand one saves on the wind tunnel testing, on the other hand one has to build up massive Monte Carlo simulations to figure out the best adaptive game for every flight condition, for every uncertainty. Basically, the price of the software development was growing on the other end. So a fundamental question that came up, so how to design adaptive flight control systems that would be captured, that would be capable of adapting fast without losing robustness, right? The JDAM example you see here is by Air Force Production, so it basically uses an adaptive controller developed by our group at Georgia Tech. But the fundamental question that came up basically is what drove our research already at Virginia Tech, so we came up with the so-called L1 adaptive control architecture. L1 stands for a spatial norm in a specific space. So the key idea here is the decoupling of the estimation and control loops. So we were able over the years to commercialize it for different industries. What you see here is the Raymarine Evolution Autopilot, Intelinair drone, Caterpillar, Statoil. We had lots of intensive testing. So more details are in our book. So, and with this architecture, we were able already to tackle major challenges in different industries. So the underlying mathematical problem is reduced to some non-convex optimization problems, and I won't go into the details of solutions of this. So just putting things into the historical context, and this slide has been adapted from the Boeing company. So if starting 60s, as I said, until 2005, Boeing was able to transition adaptive control to various platforms through various programs. Everywhere they were limited by the slow pace of adaptation, expensive gain scheduling, so we came up with a fast adaptation with single design, and we were able to take a few major airplanes. Here what you see is the UAV platform of Naval Postgraduate School. Here is a subscale 757 at NASA we did, and the other one is the Learjet that we flew, and I will go through some flight tests just to keep things more entertaining. So in 2007, NASA came up with this aviation safety program from US Congress, where the challenge was to ensure that the flight control system will be always predictable, repeatable, testable, safe. The four buzzwords were put forth. What you see here in green is the normal flight envelope, where the pilot will usually fly. The gray corresponds to the flight envelope that one can have from wind tunnel data. In the blue area, it's not clear whether the airplane is controllable or not. The best example I give to illustrate this is my car accident in Illinois during the first winter when I moved. So basically I had no experience of driving on ice, and the first ice storm hit, and I had a car accident because I didn't know how to handle my car in unpredictable circumstances. So in unpredictable circumstances you tend to provide overcorrective actions, and that can cause basically an accident, but as you see I'm alive. When that happened on an airplane, I was driving at 5 miles per hour, so I couldn't have died. But if it happened with an airplane and the pilot tries to provide the corrective action, he ends up with so-called pilot-induced oscillations, which is the main cause of aviation crash. So in the blue area, in terms of angle of attack and side slip, it's not clear if the airplane is controllable or not. These are the conditions that for which you can try maybe to train the pilots to fly there. But you don't want the safety of the aircraft to depend upon the skill level of the pilot. You want it always to be predictable, testable, safe, and repeatable, right? So NASA said, can we come up with a flight control system that will take large class of uncertainty and yet provide a controllable aircraft to the pilot? So NASA came with a serious commitment, kind of. They built this subscale aircraft, which was 5.5% geometrically and dynamically scaled model. I think they paid $1 million to Boeing to get the aerodynamic database. They spent 5 years on correctly downscaling. They even did not want to include a small computer board on it because it would have violated the mass scaling property. And I mean, through a major competitive program, we were awarded about $1.5 million to test our controller on it. So, I mean, the key idea here was to build a flying wind tunnel. Why flying wind tunnel? Because when Boeing tests advanced aircraft, advanced control methodologies or anything, they have to go through wind tunnel to reach the real airplane. And despite all the advancements, from wind tunnel to real airplane, a flight controller is not moving. So 50 years they are still using the controllers from 50. So the credibility level is not enough, the fidelity level is not enough. So NASA said we'll build a flying wind tunnel, by which they meant that they will have a pilot on the ground flying the subscale airplane, which will be a 1 level higher fidelity as compared to the wind tunnel. So they built this subscale model, provided it to all the researchers who were part of that program, including the Boeing company. So everybody got the same 4-degree angle of attack, 80 knot equivalent airspeed flight condition to design their controller, and the pilots were going to test it, to put it into various challenging conditions to see how the flight control system could handle it. So I mean, the program was very exciting, being a part of it, but it was challenging. 6 a.m. there, 8 p.m. out of the runway, all day without bathroom. So it was really, it was part of the challenges, right? So these runways, so I mean, we're spending 2 weeks there just to make sure we get the fair chance of fair competition. So the airplane is being taken off by the safety pilot, who then handles the controls to the research pilot. The research pilot has 40 years of experience as a Boeing pilot and is now working as a research pilot for NASA. So he speaks pretty well our language. Like he would come and say, oh, I have more damping here, or I want more kind of aggressive maneuver, and he was able to spell out everything in terms of control specifications. So here is where I got first time exposed to really rigorous engineering. We had a 700-page book by NASA provided for all the specs that we had to watch out, to kind of be very conservative in testing every new condition. So here is the mobile operation station, inside which we had 3 rooms. This is the pilot. Next to him is a flight test engineer who is capable of injecting failures on the airplane. And the pilot is testing and just giving rankings to the controller. And I will go through some of the rankings as well. So what was also important through this testing, NASA was trying to collect more data, as the role of the data was emphasized here. So the more data was giving opportunity to update the aerodynamic models and to have better fidelity, higher fidelity models for various challenging conditions that the aircraft was going to test. And now you will see the system identification group that's recording actively the data, because the data is what makes it all the research by the end of the day valuable. So this is the pilot station. Next to him are the system ID group people. So here we are the system identification people on the last room. In the last room we were sitting with muted microphones, so we could hear the pilot talking, but we couldn't basically talk or comment.